correlators.
I forgot.
Right. So yeah, the techniques which I'm going to use actually are very general, and it applies to all different holographic defects with different dimensions p. Okay, and that's actually the reason why we want to think of these objects as defects, because it allows us to tackle different problems with very different physical nature. Using the same set of techniques, so we don't need to come up with new tricks to tackle different problems. Now, I also want to argue that these giant graviton correlators, as defect correlators, are especially interesting for at least two reasons. So the first reason is usually when people study correlation functions, people focus on correlation functions of light operators. And studies involving heavy operators, which they are much more difficult. And Francesco did quite a few impressive work about heavy operators, but in general, in the literature, the results are far fewer. Okay, so that's one reason why we are interested in these objects. Another reason is I just mentioned that these giant graviton correlators, they admit dual interpretations. So that's quite rare because you can view these objects in two different complementary ways. So they can be both viewed as correlators of local operators, but we can also view them as defects. And we will see why these complementary perspectives are useful. Okay, so I hope I have convinced you that these giant graviton correlators are interesting to study. But unfortunately, we don't know much about these objects. So, so far, most of the studies about giant graviton correlators focus on the case where you have two giant graviton operators and one extra light operator. But I would argue that this case is somewhat less interesting. Because we are in the CFT and 3-point functions are essentially fixed by symmetries to an overall number. So all you can learn from looking at these 3-point functions is essentially just one number. The next simplest but non-trivial case would be you have where you have two giant gravitons and two light operators. But not much has been studied about this 4-point function. So far, all these examples studied are in the weak coupling regime. Oh, let me get rid of this. Okay. And so in weak coupling, these people have computed using perturbative techniques of these 4-point functions to up to 3 loops. And in the opposite strongly coupled regime, actually there's no result by now. And the only thing we know at strong coupling actually comes from the so-called integrated correlator. So this is some result obtained from localization techniques. Localization can compute a certain integrated. So basically, you take the correlator and integrate it with some measure. So ultimately, you get a number. And this number actually, you can study, you have a number for arbitrary gauge group rank and coupling. So you can go to the strong coupling regime. And so this is interesting. On the other hand, it's still just one number. And so far, it's only possible to get this integrated correlator for the simplest such 4-point function, where these light operators are the superconformed primaries of the so-called Swiss tensor multiplet. Okay, so what I will present in today's talk is results for these 4-point functions in the strongly coupled regime. So we are going to use some techniques called bootstrap techniques to compute these 4-point functions for not just a special kinematic regime, kinematic configuration, but for arbitrary kinematic configuration. And we are going to obtain all these 4-point functions for these light operators with arbitrary conformal dimensions. Although the main part of the talk is going to be in this infinite de Hooft coupling regime, the strongly coupled regime, but we are going to find there's some very interesting hidden properties in these correlators. And these hidden properties actually also turn out to be hold in the opposite weakly coupled limit. Okay, so are there any questions before I go more into the specifics?
I have a curiosity on that question.
Yes.
When you said that on defects we can dynamic degrees of freedom. And how can I mention dynamic degrees of freedom on the -1 equals -1 defect? Is that a physical interpretation or?
Yes, for this case, right?
Yeah, exactly.
Yeah. So right from the boundary perspective, it's not very clear. But from the bulk perspective, it's actually easy to see because you actually have an S2, which sits at the point. So you can imagine they are localized the degrees of freedom. Well, I mean, in this case, it's already full, so not really. But you can have like bulk fields, which are localized and you are put back to this. Yeah, so they introduce vertices that can interact with other parts of the space. Yes. Yeah, thanks. That's a very good question. Any other questions? Okay, so now let me be a bit more precise. So as I mentioned, there are two types of operators we want to consider, heavy and light. And for the heavy operator, I'm considering in particular the so-called maximal giant graviton operators. So they are constructed from the 6 scalars of n equals to 4 supermills. So these are the phi's. And here I also introduce these peaks. These are the polarization vectors for the SO6 asymmetry. These are null vectors. And this combination makes automatically half BPS, okay? And they're constructed by considering the n times n determinants of the gauge group. So the operator dimension is delta is n, and it transforms in the 0 and 0 representation by SO6. And therefore it's half BPS. And from string theory, so this is the field theory way to look at it. From string theory, we can construct such operators as D3 brins wrapping an S3 instead of S5. Now, in addition to these heavy giant gravitons, we also have light supergravitons. So here, by super, I don't mean they are fermionic. I just want to distinguish them with the real gravitons, which have spins. So these are actually just scalar operators. So they also are constructed from the same combination, but instead of taking determinant, I will take copies of these guys and I take the trace. Okay, so these operators, they will have dimension delta equals to k, and they transform in a 0k0 representation of SO6, and therefore they also satisfy the BPS relation. They are protected by superconformal symmetry. And the bulk interpretation of these operators are the particular modes of the 10-dimensional supergravity fields. Okay, so these are the operators we are considering. And the observable we want to study in today's talk is the 4-point function of 2 of these light supergravitons and 2 giant graviton operators. And I'm inserting the giant gravitons at locations 3 and 4, and the light ones are inserted at 1 and 2. Okay. Now, as I mentioned, we are going to use a sort of bootstrap approach to study these objects. And for this bootstrap approach to work, it's important to take advantage of the symmetries of the system. So I'm going to spend the next few slides to discuss the kinematics of these 4-point functions. And I will discuss the kinematics from two complementary perspectives, first as 4-point functions, and then as defect 2-point functions. Okay, as 4-point functions, actually, there have been lots of studies of these half BPS 4-point functions since the early days of VDSFT. And superconformal symmetry will tell you that the 4-point function the 4-point functions, they have to take this special form. So the 4-point function can always be written as the sum of two parts. The first part is the 4-point function in the free theory. And then there is another part which is called the reduced 4-point function. So which is denoted here by this K here. Now, in front of this K, there's also some kinematic factors. So here, this Tij, I define them to be just the Ti times Tj, where we recall T is the is a 6-dimensional asymmetry coordination vector. And Xij is just Xi minus Xj, okay? Also, there is a factor R, which is determined by superconformal symmetry. It is the combination of these of the conformal cross ratios defined here and asymmetry cross ratios. And this form of the result in the literature is known as the partial non-renormalization theorem. The reason people call it partial is because it's truly non-renormalized. You only have the free theory results, but here it's not unrenormalized. It actually depends on coupling. So the coupling dependent part is in this reduced correlator K. Okay. And as a side comment, let me mention that if you consider a certain what people call a twist, where you set the asymmetry cross ratios to some special value with respect to conformal cross ratio, you will find the second factor is gone. And the first factor just becomes a meromorphic function. Only depends on Z and alpha, the altitude of the cross ratios. So this is known as the Kähler algebra, but we will not quite use that, so I will not go into details. And the final thing about this 4-point function is that this reduced correlator, it has the same crossing symmetry as the original 4-point function itself, but the difference is that the quantum numbers are shifted. So the conformal dimension of this reduced 4-point function is shifted upwards by 2. And asymmetry charges will be shifted downwards by 2. We will see later that this is actually a quite important point. Okay, so this is the kinematics of these 4-point functions from the 4-point function perspective. Now, let's try to look at it from the complementary defect perspective. So, first of all, to define a defect 2-point function, we need to divide the 4-point function by the giant graviton 2-point function. So why is this a natural thing to do? So one motivation can be the following. So usually when we consider defect 2-point function or defect correlator in general, we don't have, in this correlator, we don't have information about how heavy the defect is or how much charge it's carrying, right? So if you just look at the 4-point function, apparently carries the charges of these two giant graviton operators. But if you divide it by the 2-point function, at least superficially, you want to see the dimensions and charges. But this 4-point function apparently still depends on X3, X4, T2, T4, so we need to be a bit more careful. So to see this in more detail, let me introduce the projectors. So usually when we when we try to describe a defect, we would say defect is extended in some dimension, let's say X1, yeah. But it's equivalent to use projectors to do the same thing. So you can define some projector which projects the space-time to the direction in which the defect is extended and also to the orthogonal space. And this language is actually more advantageous because For example, if you go to like p equals to -1, it's not clear what do you mean by in which direction the defect is extended. And in order to define these projectors, it's useful to use the so-called embedding space. So this is to go from the 4-dimensional physical space R4 to 6 dimensions. You add 2 more dimensions. One is space, another one is time. The point of doing that is conformal symmetry is linearized in the 6-dimensional embedding space. So it's linearized at just rotations. So anything that's conformal invariant just becomes a rotation invariant in this high dimensional embedding space. Okay, now using these embedding vectors P from points 3 and 4, I can construct this combination N. And you can easily check for yourself that N times N gives you N. So this is indeed a projector. Now, this is space-time part. So for the R-symmetry part, I can define something similar from these 6-dimensional R-symmetry correlation vectors. But I'm going to do it in a slightly different way. So I'm going to take 1 minus basically this thing with P replaced by T. So at this point, it seems a bit weird, but later on, we'll see why this is actually a natural definition. Okay, now I want to point out the geometric meaning of this N and M. So this N, you can check if you multiply N by P3, you get back P3. And if you multiply it by P4, you get back P4. And therefore, it is a projector projecting the space to space spanned by P3 and P4. But if you do it for M, you find that M times T3 is 0. And similarly for 4. Therefore, M, the geometric meaning of M is that it projects to the space orthogonal to the plane spanned by T3 and T4. Okay, now using these projectors in embedding space, you can see, you can easily figure out, let's say, one-point function. So in embedding space, these operators actually define the projective way. So you can rescale P by lambda, then it's equivalent to, so O of lambda P is the same as O of P, but you need to multiply that by lambda to the minus K, and similarly for the asymmetry part. So using just P, T, and M and N, you find there's not much you can write down for one-point function. By the way, for these defect correlators, I'm using like double brackets to distinguish from the defect-free case. Okay, so for the one-point function from these ingredients, the only invariant object with the wanted scaling property is this combination. And if you substitute in the definitions and express everything in terms of T and X, this is what you get. And you can quickly realize that this combination is nothing but the 3-point function O with 2Ds divided by the DD 2-point function. Okay. So in particular, this 1-point function coefficient is nothing but the 3-point function coefficient. Okay. And of course, on the right-hand side, you know from our usual knowledge of CFD that everything is fixed by symmetry up to a number. So these two perspectives are consistent. Okay. Also, this 1-point function tells you that for the 4-point function, we should also similarly divide by 2-point function in order to define a defect 2-point function. Okay. Now, for these defect 2-point functions, symmetry is no longer powerful enough to completely fix the correlator for you. The reason is because with two operators, we can write down more conformally invariant and asymmetry invariant objects. So for the conformal part, we can write down P1.P2, which essentially is just x squared to squared. But you can also insert in between this projector N. And here, actually, A and B, they can take the same or different values, it doesn't matter. And similarly, for the asymmetry part. And because we can have these more of these building blocks, you can now write down cross ratios, which are rotationally invariant and also scaling invariant, because you have the same number of pi showing up both in the numerator and in the denominator. So from the defect perspective, this KC and Chi, these are the natural combinations you can write down. And you can write them in terms of xij squared. And these can be expressed in terms of u and v, which are the usual 4-point function cross ratios. And of course, what I'm saying here is it's not surprising, because I mean, after all, it's a 4-point function. But it's nice to see it from a slightly different perspective. Okay. And finally, we are going to use this statement from 4-point function, right? So you can write out the free part plus a reduced part. And we just divide it by 2-point function. Now the defect 2-point function, which I'm denoting here by G, also splits into 2 parts. So this is the free theory defect 2-point function times the reduced 2-point function, which I'm denoting here by H. And this H, again, it has shifted quantum numbers. The dimensions becomes K1 plus 2, K2 plus 2, and asymmetry becomes K1 minus 2 and K2 minus 2. And in particular, for the lowest KT levels, KT level, which is K equals to 2, you find it's actually neutral. The reduced object is actually neutral on the asymmetry. Okay. So this is as far as we can go by just looking at the kinematics. And in order to actually compute these correlators, we need a bit of dynamic input. And in the strong coupling regime, the input comes from the supergravity description. Okay, so via ADS-CFT, these giant gravitons are described as these 3 branes wrapped on an S3 instead of S5. And in the ADS factor, it's going to trace out a geodesic trajectory, which is R. And also this S3 spins around the S5 to give it angular momentum so that it carries R charge. Okay. And the action is the usual one. You have the dBi part, and then you have a Wessel-Miller part. And now to describing more details, then you give the metric, which is written in such a way to manifest the geometry. Okay, so here I've written the ADS phi part into 2 terms. This tau is parameterizing this R, and these xi, they are the directions orthogonal to the geodetic line. So this line is actually in the Poincaré coordinates. It's just starting from the origin, and it shoots upwards, perpendicular to the conformal boundary. Now for this S3, I'm describing this S3 using these YA coordinates, and there are also 2 orthogonal directions, which is Q and phi. So phi is an angle. And the maximal giant graviton correspond to the case where Q is 1 and phi is I tau. Okay, so in this talk I'm going to focus on maximal giant gravitons. For non-maximal giant gravitons, so Q doesn't need to be 1.
Can I have a question? Yes. Is there a way you can turn this into black holes by increasing the MLR or something like that?
So this is not heavy enough, so it doesn't back react to the geometry.
If I put many of those together, like I increase your n in front of the D3 brane action, I put many of those together.
Sorry, this n is the gauge group.
Sorry.
Yeah, so but yeah.
But still, I could put KD3 branes.
Right. So you can also consider heavier objects,
right,
which correspond to black holes.
They will also be BPS also.
Yes. So this is what Francesco considered. Right.
But for BPS, I think you never get a black hole. You always you don't have enough entropy for whatever configuration of the branes you use. You don't have enough entropy to generate a black hole.
So you might be like a small black hole with 0 horizon.
I think it always moves. and I think it always.
Okay, thanks for the comments. So, right, so this is the general, this is the classical solution. But on top of the classical solution, we can also have small fluctuations. And these correspond to localized fields living on this defect, okay? So to describe it, we need to do the following. So usually when we consider correlation functions in ADS-CFT, we consider only the ADS part. So we need to do a KK reduction for the internal manifold. So, and here we are going to do the same. So we need to integrate out the S3 factor here in order to obtain a 1D Lagrangian in ADS factor, okay? And here there's a small caveat, which is that if we want to say this more accurately, we also need to perform a so-called orbit averaging for the moduli space. The reason is because when I write down the classical solution here, actually this is one of the infinite many solutions because I can shift my time by some amount tau 0 and my starting angle by some phi 0, and this is still the solution. And so there's no reason to pick a particular starting value. So you actually need to average, you need to integrate out all these starting points. You need to average with respect to this module. But this is a technical detail which will not matter very much for what I'm going to describe.
Okay. Sorry, just to see, so you wrap a D3 ring around the S3 sphere to get a defect line in the LES.
Yes.
And then you interpret the ending point of this defect line as the zero-dimensional defect on the boundary, on the CFT.
Yes, so they were intersecting with the conformal boundary at 2 points.
Yes.
Right.
Okay.
Yeah.
And so you recover the zero-dimensional defect at tau equals 0?
And let's say minus infinity and infinity.
I see.
Yeah.
I see. Okay. Thank you.
Thanks for the question. So, yes. Okay. So, modulo this small technical caveat, and you do this S3 integration, you get this 1D Lagrangian, and then 1D Lagrangian has the following form. So it's an expansion in the number of fields. So here I'm denoting each term with indices m and n as a term that contains n defect fields and n bulk fields, okay? For example, if you look at 2, 0, that is just the connect term on the defect because it carries 2 defect fields and 0 bulk fields. And this connect term will give you the spectrum of the defect fluctuations, which I'm summarizing here. So if I want to be more precise, I should say that this is not a full spectrum. I'm only keeping the fields which are relevant for our computation 2-point questions. Now, in addition to this defect fluctuation, we also have, of course, the fluctuations in the bulk ADS-5. And the defect is not going to do anything to the bulk. Therefore, we have the same spectrum which people obtained in the 80s. Okay. Now, we can also consider other terms, for example, 0, 1, that correspond to one bulk field and single defect field. So this is sort of a tadpole vertex of a bulk field ending on the defect. Okay. And 1, 1 describes the interaction of defect field with bulk field. And finally, we have 0, 2, which is just the direct interaction of 2 bulk fields. Okay, now let's go slightly more into the details. So here I'm showing you L01 and L1, 1. So the L01 contains just a bulk field, and you can focus on these fields, bulk fields, which carry spins, and you realize this actually takes the form of a massive particle in ADS, minimally coupled to the background gauge fields and gravity. Okay, so so you can do this exercise I outlined earlier, and you see this result, which agrees with your expectation. Now for this defect bulk interaction, there's an interesting feature I want to point out. So these S are the bulk field, and these K's, they are the defect field. and you find that they are actually terms with just a single derivative. This is a special feature for 1D defect, I mean 1D in the box sense. And this is because these derivatives along the defect, they're already invariant. You don't need to construct with anything. But for higher dimensional defect, you need at least 2 of these. Now, in principle, we also need to include this term with 2 bulk fields in order to compute these defect correlators at tree level. But it's actually known in similar setups that the direct supergravity calculation actually does not give you the right answer. So we are not going to look into that here. And also, it will be unnecessary because from the bootstrap calculation, we do not need this term as the input. In fact, we will not even use like all these coefficients, like the C's and D's, as the input of the calculation. Any questions?
So when you say gives the wrong vertices, you mean because if you take the limit of the you set them?
Yeah. So for example, we can consider like a Wilson loop 2-point function.
Yes.
In the bulk, it corresponds to the wordsheet of the string.
Yes.
Yes. So you can actually do this expansion and you can get 0,2 type of vertices. And you can compute their contribution.
I see.
You find that this is wrong because the answer you get does not satisfy superconfirmed identity. So it's quite subtle. It's not quite known what went wrong. But so this is, well, the loop is one example. Another example is if you put n equals 4 supermills on RP4, you also find the wrong answer.
Yes.
Yeah. Okay, so let me just tell you what we need from this very schematic supergravity analysis. So what we need is the following these following pictures. So we are going to compute these 2-point functions at the leading non-trivial order in 1 over n, in fact, just order 1 over n. And those correspond to some tree-level processes. And there are 3 types of diagrams which will contribute. So we have 2 types of exchange diagrams. So in this diagram, you're exchanging the field in the bulk, not on the defect. And here you're considering exchange with a diagram where a field living on a defect is being exchanged. And finally, you have the contact with the diagrams where these 2 bulk fields interact directly at the contact vertex localized on the geodesic line. Okay, so in principle, we could work out all the vertices and try to compute, but this is not the best idea for 2 reasons. One, you need to work very hard. It's not an easy calculation. Second, some vertices we know they're wrong, so actually it's impossible to do it. So instead, we are going to use Bootstrap to compute these correlators. So this strategy actually was first introduced for defect-free CFTs, where we look at 4-point functions. And recently, that has been extended to include defects. So, a defect with 2 operators inserted away from the defect. And the strategy has been actually applied to a number of different setups. And for what I'm going to tell you, the algorithm is actually similar. And I will try not to get into the very technical details, but I will just try to outline the general idea. Okay, so the general idea for bootstrapping 2-point functions is actually very simple and straightforward. So basically, we first want to make an onset of the tree-level 2-point function and the sum of all the possible Witten diagrams. The number of Witten diagrams is actually always finite if you fix K1 and K2. Okay, and instead of using the precise vertices to fix the contribution of each diagram, we are going to leave them as unknowns. And then we are going to use superconfirmed signature to fix these unknowns. And this will fix for you the correlator. Okay. And the onset we are going to make for the 2-point function follows from this picture here. So we can divide the contributions, the answers into 3 different contributions. We have the exchanges in the bulk, defect, and we also have the contact interactions. Now, just a little bit more detail. So the exchange contributions can be written in the following form. So let's first look at the bulk part. So it's has 3 things. So this E is this exchange written diagram here. And it's also multiplied by this Q here, which is some asymmetry polynomial. So the way to think about these Qs is that these are the asymmetry analog of these exchange written diagrams. Because each field carries irreducible asymmetry representation. So in this exchange process, asymmetry is also exchange. So you need something to capture that information. And this is this polynomial Q here. And this mu is still some numerical factor, which we will put in our ansatz as unknown, okay? Now the same story for the defect channel exchange. Here, in order to emphasize the point, I have split these contributions into 2 parts according to the so-called transfer spin. So all these defect fluctuations, they're scalars. However, they can carry non-trivial angular momentum for the numbers transfers to the defect line, okay? So here, this part is spin 0, this part is spin 1. And for the spin 0 guys, because we saw earlier that these vertices, they can contain 0 or 1 derivatives. Therefore, these exchange written diagrams can contain up to 2 derivatives, okay? Okay, so, for these exchange parts, we can actually also evaluate these diagrams using standard techniques in the literature. So so this is quite a technical point. I'm just going to tell you the end result. The end result that all these exchange written diagrams can be evaluated as a finite sum of these contact written diagrams. And these contact written diagrams denoted by C here can further be evaluated in a closed form as the 2f1 function of the conformal cross ratio B. Okay, and finally, for the contact part, we are going to include all the possible asymmetry structures. So we write down a generic conformal, generic asymmetry polynomial, and it's multiplied by a contact written diagram with 0 derivative in its vertex. The reason that we assume that there are no derivatives is because derivatives actually are associated with the high energy behavior of these correlators. So if you add more derivatives, you find it's enhanced in the high energy limits. And in our case here, which is the supergravity limit, we do not expect the contact interactions to dominate the high energy limits. And therefore, we want to make this assumption that you have the lowest number of derivatives. Okay. Okay, so right, so we have an ansatz, we know how to evaluate inverse cross ratios. And finally, we import superconformal symmetry conditions, as we seen earlier, and that will fix, turns out very remarkably, that fixes all the coefficients up to no row factor. So essentially for each K1 and K2, we have an unfixed number, okay? Now, these numbers actually cannot be all independent. The reason because we can choose this number, for example, to be one of these mu's in the bulk channel. And these mu's actually, they have the meaning of a 3-point function times 1-point function. And you actually have the same one, you have the same field being exchanged in different K1, K2 2-point function. And therefore, you can actually relate all these overall coefficients and reduce them to just 1. Let's say for K1 equals to K2 equals 2. So ultimately, there are no free parameters left. Okay. Now, just to give you some idea what the result look like, so I'm showing you here the defect 2-point function for K1 equals to K2 equals 2. So as we discussed earlier, you can write the result into a free part, which has this very simple rational form, and also reduced correlator. The reduced correlator actually is still quite simple. You find it's it contains at most a single power of log p in its form. Okay, so this is for the simplest correlator. You can also similarly consider higher values of k's. The results are similar but longer. Okay. Now, before I go on and point out properties of these defect two-point functions, I first want to mention a few very non-trivial consistency checks. From our results, you can obtain the free correlators, but in the free correlators, actually, they are not difficult to compute because they can just compute them in the free theory using working charges. So this was carried out by these authors for the case where K1 equals to K2 equals to P, and we find our supergravity calculation agrees precisely with the free theory calculation. So that's the first check. Another check is that once we've computed these two-point functions, we can go back to look at these bulk exchange Newton diagrams, and their coefficients gives you one-point function times three-point function, and three-point functions were already known like almost 30 years ago. But these one-point functions actually can also honestly compute from these vertices, right? And this information, these one-point functions actually were never used in this algorithm. So that provides another consistency check. And very nicely, we find from the two-point functions, we get exactly the one-point functions you get from directly computing, from direct computation. Okay, and finally, let's go back to this integrated correlator. So you can take these also two results, which correspond to K1 equals K2 equals 2, and then you take the strong coupling limit. You find the answer is precisely the same as taking our H22 and integrate with the measure they gave. Okay. So yeah, so that's the result and how it's checked against the other independent calculations. Now, let me point out some very interesting features in these supergravity two-point functions. So we find that these two-point functions, they actually exhibit a very remarkable hidden symmetry, which is similar to the hidden conformal, the 10-dimensional hidden conformal symmetry first pointed out by Simon Karenholtz and Anko Chin for the 4-point functions of light supergravitons. So let me first briefly review what is this hidden symmetry they observed. So what they found is that if you have 4 light supergravitons, you can also write the answer as a free part and a reduced part. And this reduced part can actually be repackaged into a single generating function. And this generating function actually is obtained from the simplest correlator, where the KK level has its lowest value 2. Okay. Now, as I already mentioned many slides ago, a special feature of this 2 4-point function is that it's a function of the 4-dimensional distance xij squared only. Okay, and their prescription for promoting the simplest 4-point function into a generating function is to uplift these 4-dimensional distances into 10-dimensional distances. Okay, so more precisely what they did is that they could.
Can I go there?
Yes.
So that symmetry is just the fact that 10-dimensional supergravity at low energy doesn't have any scale, no? So it matches the calculation of supergravity in 10 dimensions.
Actually, the feasible interpretation is not clear because the reduced correlator itself does not correspond to like a sum of Newton diagram.
But when you say 10-dimensional hidden conformal symmetry,
Yes,
it's 10 dimensions, presumably because you're recovering the to be 10 dimensions.
It's not quite that. I think it's like the reason is more like superficial.
Okay.
So the reason is because basically you combine this 6-dimensional embedding vector with a 6-dimensional asymmetry vector to get a 12-dimensional vector, which is, 12 is the 12 is like 10 plus 2, so that's embedding space for R10.
Yes, yes.
Yes. But there's actually not really a physical interpretation.
I mean, that's how you would combine like the R symmetry is KK momentum on the sphere, so I would add it on everything.
Yes, but yeah, but it's actually not very clear, like for example, how to systematically to go to even more points. Yeah, so I would say like so far, like it's actually not very clear, and actually it's also not a unique property of gravity. It's also for like, ADS5 supernova, so ADS5 has 3. Yeah.
Has anybody done something similar in ABJM?
Yeah, so people haven't found any, and I guess the anticipation is no, because in all these models, people where we have this sort of behavior is where the radius of ADS is the same as the radius S. So you need the background to be conformally flat. Well, for ABJM, it's not, like it is 4 times S7, they have different every time.
Oh, okay.
Yeah.
So they are the same order of magnitude, but they are numerically different.
Exactly,
Okay.
like 2 to 1, yeah.
Okay, thanks.
Yeah. So, okay, so the prescription essentially is the following. So, this is xij squared, and you replace P by this higher dimensional vector Z, and this is xij squared minus 2 Tij, and this is the invariant distance in 10 dimensions. And doing so to the lowest correlator, you get a generating function, and all you need to do is to expand with respect to Tij to get higher the 4-point reduced correlator of higher values of Ki. Okay, so that's the what these people found a few years back for correlators with just light operators. Now, their prescription does not work for our case. You can try, but you find it's actually not working. And the reason is because we should not think of giant gravitons as local operators, at least in what we are doing here, but we really should think of them as defects. Okay, and we still can find such a higher dimensional symmetry by modifying their prescription. So what I mean by that is that we still combine P and T to form these 12-dimensional vectors. But we only do this replacement for 1 and 2, okay? For 3 and 4, we are not going to do anything to this piece, but we will do something to the projectors formed by P3 and P4. So this projector N, which is formed by P3 and P2, in this uplifting procedure, we are going to replace it by N plus M. So I remind you, this M is the asymmetry projector, okay? So in addition to this uplifting projector, we of course also uplift P1 and P2 to be Z1 and Z2. So at this point, so this is just a prescription. I will explain why this is a natural prescription in the next slide. Okay, so for the moment, I'm just telling you that there's these rules. You can follow these rules, and you implement them on the simplest correlator H22, and you find some object. But this object is actually generating function. So if you parallel expand in T1 and T2, so here I'm doing it with respect to I'm doing a rescaling by lambda1 and lambda2, and expand with respect to these lambdas, just for this expansion to be a bit simpler. But essentially, we are expanding with respect to the t's, and you find the Taylor expansion coefficients give you precisely this HK1, K2 computed by the supergravity bootstrap. Okay, so this gives you a defect version of the hidden conformal symmetry found by these guys. Now I will explain why this prescription is a natural one. Okay, so let's go back again to their story. So in their paper, they actually give a intuitive but not very precise picture for how to think of this inner performance symmetry. So what they proposed is that you can think of it as doing a wire transformation from ADS pi times S5 to R10. And this is possible because these two factors, they have the same radius. Now, these correlated functions under this wire transform will become some scatter amplitudes in 10 dimensions. And I should also mention that, you know, if you just do a wire transformation, it's actually not R10 because there's also conformal boundary, but if you're away from the conformal boundary, it looks like an R10. Okay. Okay, now let's go to our story. So in our story, we have these light gravitons, but we also have these giant gravitons. And in the string theory description, these are these three branes wrapping an S3 in S5. So when we do a wire transformation, in addition to getting this R10, we also get an R4, which corresponds to the body volume at this D3, right? So there's R part, and there's also this S3 part. And these 4-point functions will correspond to the form factor of two closed strings, closed string modes, scattering with this D3 brane. Now, if you recall how I defined these projectors, so this N for the conformal part projects to the defect, to this R. However, I defined M to be a projector that projects to the subspace orthogonal to T3 and T4. And the orthogonal space actually is precisely this R3, right? And this 4-dimensional space is the product of R times this R3. And therefore, you know, in order to define a projector for this 4-dimensional space, it makes sense to add up these two projectors. So that's why its prescription I replaced N by N plus N. Okay. And so because I don't have time to go into details, I just want to point out that, so although I'm doing here everything in collision space, you can also look at these results in the so-called mailing space. The mailing space, you can think of that as just the momentum space for ADS, and there's also defect version for that. And there, you can make more manifest the scattering amplitude nature or scattering form nature of these objects. And here we'll also see that the hidden symmetry acts in a very natural way. Okay. Now the last thing I want to mention is about weak coupling. So far I've only talked about strong coupling, but quite surprisingly, we find, or maybe not that surprisingly, that what we observed actually also has applications in the weak coupling regime. So the reason that it's not that surprising is because for the 4 supergraviton case, Simon and Frank, they observed that the stem replacement also takes place in the weak coupling region, but in a slightly different way. Okay, so if you look at half BPS operator 4-point functions in weak coupling, there's a method to compute loop corrections using the so-called Lagrange insertion method, and this method will naturally define integrand at each loop level. So what Simon and Frank found is that if you do the same replacement, not for the whole correlator or the integral, you do it for the integrand, it also allows you to package all the integrands into generating functions. And what we are finding in giant Graviton correlators is similar, is also similar. Okay. So for these giant Graviton 2-point functions, you can also use Lagrange insertion to compute their loop corrections. For example, at one loop, the integrand takes the following form. In general, if you go to Lth loop, the integrand will be a defect correlator with L plus 2 points. And the extra points we're supposed to integrate over are x pi to xl plus 4. Okay. And if you focus on the case where it's 2, 2, K1 equals to K2 equals 2, this L plus 2 point where all have conformal dimension 4 and is asymmetry neutral. Okay, now how do we see hidden conformal symmetry? So the prescription we propose is the following. So first of all, you need to do something about the additional points where you do inversions. So we also lift them to 12 dimensions, but instead of giving them some potential vector, we are just going to set this component to be 0. And then we extend our transformation rules here by allowing these A and B to take more values. So initially it was just that A and B can only be 1 or 2, but now we allow them to also include 5 and all the way to L plus 4. In other words, we allow them to take values for all points other than 3 and 4, which correspond to defect. Okay. So you do this to the lowest I to 2 at each loop L. What you get is the generating function for the integrands. For example, at one loop, you start from this, you do this replacement rule. This is what you get at the generating function. Now, if you expand with respect to lambda 1 and lambda 2, you will get IK1 and IK2 at one loop. And we check this structure at both 1 and 2 loops with the results available. Okay, so now let me wrap up my talk. So I think there are many things we can try to explore along the lines of today's talk. So first of all, we only looked at in our paper the so-called maximal joint gravitons, but we can also similarly look at the so-called non-maximal joint gravitons. So these are subdeterminants instead of just determinants. So instead of dimension n, they can have smaller dimensions. And also, we can look at the so-called dual joint gravitons. The joint gravitons we consider here, they correspond to the branes wrapped in the S3 instead of S5. But you can also have dual joint gravitons wrapped in the S3 in the ADS5 factor. Another thing we can do is to extract the data contained in our results. For example, you can extract OPE coefficients, and it'd be interesting to reproduce these results using other techniques such as interconvertibility. In the talk today, we considered correlators with just one defect, but actually it would be interesting to look at more defects, and there have been very few studies on that. And I would argue that the joint gravitons are the ideal setup to consider more defects, because you can, for example, look at 4-point function of 4 joint graviton operators, and that will give you 2 defects. So you can consider the interaction of these 2 defects. Sorry. Yes. And finally, there are actually already like quite standard tools in the literature, which allows you to go further to look at loop level supergravity correlator and also stringy corrections. Also, it'd be interesting to look at one defect, 2 giant gravitons with more light operators, and this is interesting from the amplitude perspective, because usually in amplitudes you see like non-trivial features at higher multiplicity. And finally, I think it's obvious that these bootstrap techniques should also work for series in other dimensions, such as ADS4 times ADS4 and ADS7, and we should expect to get similar results. Maybe not for hidden symmetry, but you can definitely work out these correlators. So let me stop here, and thank you very much.
So are there any questions we can ask?
So you're saying you don't expect this any analogous of the conformal symmetry either in ADS3 or in ADS6, right?
Well, I think if you have like the same, like this background is conformally flat, I think you can.
I don't know, I don't know which cases satisfy that criteria, so it is factors 5 is 1, and what are others?
Yes, for example, 83 times 3.
83 versus 3.
Yeah.
And then you would expect a 6-dimensional hidden symmetry or 10 dimensions still?
6 dimension.
Okay.
So for the four light supergraviton case, yes.
Okay,
Yeah.
got it. Thanks.
Any other question?
The result is 5 times S3.
Yeah, yes, yeah. Actually, there are more. Yeah.
It's a bit unclear how you classify which.
It is factors S3.
Mm.
So how do you get that from string theory?
Yeah, so that's like when you consider also sort of defect system, you have D3 and D7. The D7 is a probe.
Okay.
Yeah, and it takes large n limit. The degrees of freedom on D7 will decouple from the bulk.
Okay. And then you expect a dimension?
Yes, exactly.
So it's always.
And it's non-gravitational. This limit. Yeah.
Can I ask one?
Correct.
So there's sometimes in CFTs you can also have defect operators which are not supersymmetric.
Yes.
Even you can have different particles which are protected by discrete charges and stuff like that. For example, say these factors RP5, we can have brains trapped in the one cycle of RP5.
Yeah.
This can be non-BPS and they're to some nice operator which has some discrete charge. Is there any way to prove those from this point of view?
I think that's a very interesting question. Yeah, I'm not sure what the answer is, but I guess one can try and see. Yeah.
So maybe I have a question. Do you think that for the non-maximal giant graviton there is a similar story, or?
Yeah, so this is something we are thinking of. Yeah, I think there should be some similar story as well, but yeah, I think we are still working on that. Because from the computational perspective, it's not that different.
I see.
Yeah.
So then I have a comment. I mean, it's known that the single particle operators, they become the giant graviton when the level, the KK level scale like n, which is the maximum you can have.
Right.
So
yeah, that's in our paper. Yes.
Yes. So I was wondering whether in many space you have tried this saddle point approximation.
Yeah, I think.
From
Yeah.
P2.
I think it's So actually, that's like the thing we did initially, but I think it should not work. Because first of all, like the 1/n counting is different. So for these giant graviton, like 2 giant graviton, 2 light particles, it's of order 1/n. But the light ones, they are of order 1/n squared. So I think the 1/n counting is a bit messed up when you go from light to heavy.
I see.
However, as you know very well, so the opposite direction is okay somehow.
But
right?
the 3-point functions, they work like giant graviton light.
Yeah.
That works as a limit of single particle light. So okay, let's see.
So yeah, as that I'm not sure, but yeah, actually, so we did the exercise you suggested, like 2 to pp, we take p to infinity. You get not this, but something quite close.
I see. I
Yeah.
see.
So yeah.
Thanks. Are questions from the chat that I can?
Can I ask a question?
Sure.
Can you go back to the slide with the word line action after you integrated S3?
This one.
Yes, perfect. Can we look at some of these terms as like, especially the contact terms that after you draw, as like the numbers for the giant graviton? Can we relate these to ideas?
Not this one? This time?
Yeah. The ones afterwards. You also draw some diagrams. So the corresponding to the contact diagram, exactly the third one.
Yes.
Can we like relate it somehow?
Relate to to what?
I think it wants to know
Love numbers of giant gravitons.
Sorry.
This and
Yes. Sorry. Yes, that's let me explain. So these are one-point vertices which appear in this part of the diagram. So you have a bulk field ending on the defect. And here you have the bulk 3 point, which was not written here, but that was already included in the usual ADS5 effective action. And now for the defect exchange, at this vertex, you have one defect field and one bulk field, and that corresponds to these terms. And finally, for the contact one, you just need two bulk field to end on the defects, and that corresponds to these terms.
Yeah. And I think the physics is the same, essentially, right? Because you're effectively just having a word line and you have these contact interactions. If instead of, for example, a giant graviton, you had like a black hole and you were doing an effective description of it, you also had a word line, you also had these contact diagrams, and you basically would have other numbers characterizing it. So I think the physics is the same as log numbers for giant gravitons.
Yes, I think it's similar. So this is like more general than this specific setup. Yeah, but here, the thing is like the probe particle doesn't backreact to a geometry. So yeah, so geometry is still is 5 times 5.
Yes, thank you.
So you mentioned that L02 is wrong.
Is wrong, yes.
Can you go back from the knowledge of the contact diagram from the bootstrap and see, for example, dependence on P is wrong, or like the 1 point function now as a function of P would be wrong?
It doesn't really affect 1 point function, so this term and this term are independent.
So is it wrong? The contact diagram, whether it's wrong in its coefficient?
I think it's
a
yeah.
function.
Right. It's missing factors. So I mean, we didn't quite look in this case, but I think Alesh looked into where's the loop. So yeah, so there he found that there are like structures which you do not reproduce by directly expanding the fit fashion.
I see.
Yeah.
Cool. So we have no more questions from the room. If there are other questions from the chat, please unmute yourself.
Hello.
Hi,
Hey.
Hey. You mentioned about string already, but I don't know. Have you looked at it? Like from million space, I guess it's just one, right?
Sorry, say again. What looked into?
The string collections.
The string equations. Yes, I mean, I guess the lowest one should be just one. Yes.
Do you know what the one means in position space?
Yes. Yeah. I mean, that I can just translate back. Yeah.
I see. Because we also compute the string collection from integrated correlator, right? So then it will be just fix the coefficient.
Right. Exactly. Yeah. So yeah, we can expand your result to higher orders in 1 over lambda. Yes.
Yeah. No, in fact, in the paper we did the expansion.
Okay. Yes. Yeah. Yeah. That's indeed. Like we can actually do a bit more because we can also take the flat space limit.
Yeah.
Yeah. Do small terms. Yeah.
Yeah. In fact, for as you just said, for the leading guy, you have two constraints. Like one is flat space, one is integrated correlator. So this will conspire, give you consistent check.
Exactly. Yeah.
And maybe next order even can be fixed. I don't know.
So too, yeah, it should be quite similar to like Wilson. I mean, Hofft-Luke 2-point function. Yes.
Yeah. Okay. You have another question?
Yeah. Maybe let me just ask a curiosity. So when you look at the operator for the light fields, are these a single trace operator or single particle operator? Or maybe it doesn't make a difference?
This is actually a single particle.
Okay.
Because, for example, you can see from like this part of the contribution. So like here, the extreme of 3-point function will be vanishing.
Okay.
It's a single particle.
So it is important to have this 1 over n correction, the mixing, right? That's important in this context.
Yes. Yeah. So indeed. Yeah. Also, like, because I mean, this is probe, it doesn't really affect what's in the bulk, and these are like modes in the bulk. So yeah. So yeah, indeed, this 1 over mixing is important. Yes.
Okay. Thank you.
Thanks.
Okay.
Okay. If there are no more questions, let's thank Xinan again for a nice talk.
Thanks.
And thanks a lot to everybody that participated, and I hope to see you next time. Okay. Have a nice afternoon. Bye bye.